Hello everyone. Welcome to lecture 3 of module 2, which is on SRAMs. In the last lecture, we saw the structure of the SRAM cell, which comprises of, a bistable element with two access transistors by which you can read or manipulate the data which is stored on that bistable element. We also saw how we can read the data. Then we also saw the constraints on the sizes of the transistor, size of the access transistor and the pull down transistor of the inverters in that bistable element, which should ensure a non-destructive read. We saw that the cell ratio, which was basically what? The driving strength, the ratio of the driving strength of the access transistor and the pull down transistor. We saw that we made, those pull down transistors stronger as compared to the access transistors so that it's a non-destructive read. The content of the SRAM cell is not flipped. We also saw how we can write data into the SRAM cell. And in that, we saw that, there is something which is known as pull ratio. And that is not a very, I would say stringent constraint. And even if you size all the transistors as minimum size, that is kind of always satisfied. So with that information, in this lecture, we would be looking at the read-write conflict in a SRAM cell. We would also be looking at, some other SRAM cell architectures, as I already told you, that apart from the 60 cell, which is the industry standard right now, we also have a 40 cell, we have a 5T cell, we have a 70 cell, 8T cell, going up to, 16T to 17T, depending upon what is the application that we are, looking at. For radiation hardness and all those things, people go for 17T SRAM cell as well to, provide immunity against single event upsets and so on. I mean, you just have those kind of different SRAM cells depending upon the application that you are looking at. So in this lecture, we will be covering one such SRAM cell in detail, which is 8T SRAM cell. Also, apart from this, we would be going through a very important criterion or a very important performance metric for any SRAM cell, which is known as the noise margin. So the disclaimers remain the same.
Last lecture, we were actually discussing the read and write operation in your SRAM cells. I was actually teaching everything with an assumption that you guys are well familiar with the concept of inverter switching threshold. However, some of the students had doubt on it. So let me just discuss in brief what exactly is inverter switching threshold and how is that important for us. So let me just draw the schematic of a CMOS inverter. So in a CMOS inverter, what we have is, we have this PMOS in series with an NMOS. So we have this PMOS, we have this NMOS, and then we have this input, which is connected to the gate terminal. We have this VDD, then we have this ground. And what is connected to its output terminal? It's a load capacitor. So why a load capacitor? Because in digital circuits, each gate on each logic is actually supposed to drive another logic or another gate. However, what you see at the input of any gate such as inverter is these two capacitances, the gate oxide capacitances of the PMOS and NMOS. So what you see at the output is a capacitance. This capacitance can be the intrinsic gate capacitance of PMOS and NMOS, or it can be some, if it is a very large gate, then it can be something which is kind of a combination or a sum of the input gate capacitances of PMOS and NMOS circuits. Okay. So now let us go and draw the VTC or the voltage transfer characteristics of a CMOS inverter. So on the x-axis, we have this V, which is the input. On y-axis, we have Vout, which is the output. Let us divide this x-axis into two critical points. We have this VTH of N, which is the threshold voltage of this NMOS transistor. And we have this critical point as VDD minus VTHP, where this VTHP is the threshold voltage of this PMOS transistor. Now, let us look at the case when Vin is less than VTH of N. So in that case, your NMOS is not turned on, and as such, this PMOS has like an open field for driving this Vout to VDD. So this PMOS is on, and this will charge this node V out to VDD. So till this point, that is your VTHM, the output remains fixed at VDD. Now what happens as you increase your Vin beyond this VTHM? So as you increase this Vin beyond this VTHM, this CMOS inverter becomes a tug of war game. You have this node V out. This NMOS transistor, when it turns on, will try to pull it down. So it will try to discharge it to ground, while this PMOS will try to charge it to VDD. So whoever has got a more driving strength will kind of win this tug of war, and the output voltage will kind of lean towards that. So just immediately after this V is greater than VTHM, what we have is your NMOS turns on. However, if you look at the overdrive voltage of this NMOS transistor, which kind of dictates its pull strength, which is given by Vg minus Vth, so that is kind of low. Therefore, the NMOS is not that powerful, and still this Vout is kind of very close to VDD. Although it will decrease, I mean, although our NMOS is on and the voltage will decrease, but it won't decrease much. So there is slight decrease on. As you increase your Vin further, you kind of increase your VOV for the NMOS, and it kind of pulls your node potential at this Vout very close to the ground. So it kind of decreases rapidly. So what happens when it reaches VDD minus VTHP? At this point, your PMOS turns off. So at this point, there is nothing which can drive this node voltage Vout towards VDD. So this NMOS overpowers completely, and it pulls the node Vout towards ground. So in a CMOS inverter, also we have like a tug of war game where this PMOS kind of tries to pull this node potential up, while this NMOS tries to pull this node potential down. And whichever device is stronger, that will dictate your final voltage at this load capacitor. So in general, what we do is we kind of try to make your NMOS and PMOS of equal strength. So why we do that? We do that first so that we have equal TPHL and equal TPLH. Sorry, TPLH. And second reason is we want to have our noise margins equal and high. Now another salient feature of this CMOS inverter is its inverter switching threshold. Which is given by this VM. So let me use a different ink for this, as you guys suggested. So this is given by this VM. Now what exactly is this VM? So you draw a straight line, which is kind of the curve of V equals to V out. Wherever it intersects your VTC of the CMOS inverter, this point is called VM. So what is so special about this VM? So at VM, you have your V in equals to your V out equals to your VM. So now at this point, your both NMOS and PMOS are turned on, and both of them are in saturation. Another salient feature about this VM is that close to this VM point, the inverter kind of has a very high gain. Why it has a very high gain? So let us take this point as VM. So at VM we have this as input, VM as output. Let us say that we change our input voltage by a very small amount close to this VM point. So how much does the output change? So corresponding to this input, the output is kind of here. So we changed our input by only a very small amount, which is del V in, but the change in the output here is significantly large as compared to the change in your input. So what exactly is amplification? Whenever your del V out by del V in is a large value, we say that an amplification has been obtained. So close to this Vm value, your inverter acts as an amplifier. This is a classic interview question that many of the industries ask, and you should actually be able to tell them that, okay, if you bias your inverter close to this Vm point, then it is kind of it can act like an amplifier. Okay. Now with this information about Vm, let us go back to the classic case of a bistable element, which you were discussing, which I define as flip-flop, and it was given by Professor G. Hill in his famous classic paper of 1968. So how we actually define that bistable element is something like this. So it's a cross-coupled inverter pair. Its input is kind of connected to your output. Let us say this is V in 1, this is V out 1, this is equals to V in of 2, and we have this V out 2, which is kind of equal to V in 1. Now we looked at its characteristics, which comes out like a butterfly curve. Let me tell you why exactly we call it a butterfly curve. So here we plotted our V in 1, which is equal to V out of 2. On the y-axis, we had our V out of 1, which is equal to your V in of 2. So how this curve looks like? So suppose this is the VTC of the first inverter. Now let me draw the first inverter. So let's say this is inverter 1. This is inverter 2. Let us say this is the VTC of the first inverter. And let us say that this is the VTC of the second inverter, but since it's kind of inverted, or we are actually looking at the axis in an inverted way, we obtain something like this. Since this resembles a butterfly like butterfly wings, so we call this curve as butterfly curve. So what's so special about this curve? So here the number of intersection points kind of tells you the number of states that this system can take. So here we have 3 points, point A, point C, and point B. While as we discussed earlier, while your A and B are stable points, C is metastable. What exactly is C? So C is the kind of, so if you draw like that linear curve, I have drawn it wrongly, so let me just draw it again. So if you draw this curve, which kind of tells you V in equals to V out, so C actually falls on that point, and it's kind of corresponds to the VM of both the inverter pairs. So we are assuming that your inverter 1 and inverter 2 are matched, and their VM are same. And this point C corresponds to your VM of both the inverters, and that is a metastable point. Why? If we introduce any noise, let's say delta Vn, any noise that we introduce at this point, I mean, let us say that somehow we are able to bias our cross-coupled inverter pair at this point C, and now we apply some noise. So what this noise does is, it kind of, because of the positive feedback that we have, it kind of, pushes it towards some stable state. So if your Vn is kind of acted in this direction, it will pull the state towards B. If your noise is, let's say, in this direction, towards your left, it will kind of, pull this system towards this point A, stable point A. So C is a metastable point, just because you have, these noise sources in your system which are inherent. I mean, you cannot do away with the noise. So even if you bias it at point C, because of this inherent noise in your system, it will kind of go back to these stable states. And why exactly this C is a metastable state? Just because close to your VM, your gain that the inverters exhibit is very high. That is kind of leading to this regenerative effect, which kind of sends these to these stable states. Now, let us talk about what happens to a single inverter when there is a noise at its input terminal. So let us draw this CMOS inverter over here. Let us say that there is a DC noise source, or it can be an offset, which is applied like this to its input terminal. And how your input is kind of given? It's given by this. Let's say this is your Vin. So what is the effective voltage at the input of this? Let's say the effective voltage is Vin dash. So what exactly is this Vin dash? So Vin dash is nothing, but it's equal to minus Vin plus Vin. So thumb rule, if your negative terminal of the noise is kind of placed at your input terminal of your inverter, effective voltage will be Vin minus Vn. And similarly, if you have a case where this positive terminal of this noise is kind of placed at the input of this inverter, then your effective voltage will be Vin plus Vn. Now with this information, let us look at the VTC of these two inverters in the presence of this DC offset or DC noise source. So we have this as, let's say, the VTC when there was no noise present for both the inverters. Now, when the noise is present, what happens is, if your effective input is Vn minus Vn, so your transistor was actually, so if this is VTH of N, so immediately after VTH of N, your curve was kind of going from VDD towards ground, right? So if your effective voltage that the input sees is Vin minus Vn, so now if this is equals to VTH N, the input voltage Vin dash at which this output will go down towards the ground will be VTHN plus this Vn. And in that case, what will happen is this curve will shift towards right. However, for the other case, when Vin dash equals to VTHN, you have this Vin equals to VTH minus of Vn. So it kind of shifts towards left. So now you understand that if the applied polarity is like this, where positive kind of terminal of this noise is applied to the input of the inverter, it shifts towards left. And when the negative terminal is applied towards this inverter, it shifts towards right. Keep this in mind. This will be very useful when we discuss the noise margins. Okay, with that, let us go to the read operation in a SRAM cell. So what happens in a read operation is, so first, there are these capacitances, CBL bar and CBL. First thing what we do is, we pre-charge this bit line and bit line bar to VDD. This is the first thing that we do. So these both terminals are pre-charged to VDD respectively. Then what we do is, we apply or assert the word line high. How we do that? We basically apply a pulse to this like WL, and the amplitude of this pulse is kind of VDD plus VTH of this access transistor, so that these access transistors can pass the entire VDD. If you know NMOS cannot pass perfect VDD if you apply only VDD to its gate terminal. So if this is VDD and this is VDD, what NMOS will pass is VDD minus VTH. So just to remove this problem, we actually apply a VDD plus VTH of access to this word line. Now once that is done, let us say that our SRAM cell was storing Q equals to 1 and Q bar equals to 0. So what happens is, the moment you actually turn on your word lines, you turn on your M5 and M6 access transistors. Here there won't be any problem on the right hand side because this node was already at VDD and this is also at VDD. But on the other hand, on the left hand side, if you look closely, what happens is this let's say M5, and this is let's say your M1. So this terminal is Q bar, which we call let's say VQ bar. This is VDD. This is VDD plus VTHN, and this is VDD. So this M1 is on. M1 will try to drain this load capacitor towards ground, while this VDD will try to so M1 will try to pull this node potential VQ bar towards ground. So M1 tries to pull this node potential VQ bar towards ground, while this M5, because it is connected to this VDD, will try to pull it towards VDD. So for this VQ bar, M1 tries to pull it down, while your M5 tries to pull it to VDD. So the final voltage of VQ bar will depend upon relative strengths of M1 and M5. Now what you exactly want is, since you are just reading this device, what you want is the state of device should not change. Now when the state of this bistable element changes, so if we have this bistable element like this, so this M5 is kind of applying, let's say this is M5, this was 0, this is 1, this is again 0, and you are applying a VDD over here, and M5 is on. So this is trying to pull this node towards a potential, let's say VQ bar. Now when does this kind of trigger or overpower this bistable element and switch it? When does this happen? So as I told, that when you apply this VDD for a time period which is kind of more than 2 times TP, where TP is kind of the inverter delay, it will force it and it will change the state of this. Now we don't want that, right? Because we are reading the device and we don't want the state of the device to change. So what should we do? So let us look at this bistable element characteristics again. Let us say we are kind of applying a voltage Vx over here, which is kind of coming from your access transistor. And the state of this inverter is like this, 0, 1 and 0. Let us look at the butterfly curve for this bistable element. Let's say this is inverter 1, this is inverter 2. So first we have drawn inverter 1 characteristics, and then we have drawn inverter 2 characteristics. Let's say this is our butterfly curve for this bistable element. Now this is, let's say, V of in 1, and this is, let's say, V of out 1. Now what we are doing is, apparently we are applying this Vx to this input, right? This is, let's say, our Vm. And we have another critical point, which is VTH of this N. So we have these two critical elements. So as I told, that if you are at this state A, which is this case, I mean you were initially at state A, and now we start to apply something, a voltage which is Vx. So what happens is, we start from this state A and we apply some voltage, which is kind of Vx. So as long as we do not hit this C, which is Vm, we are sure that even if the input is here, let's say even if your Vx is here, we will again come back because of this regenerative feedback, we will come back to the stable state A. However, if somehow your Vx increases to this point, I mean if it increases beyond Vm, somewhere here, definitely you will kind of, definitely what you will do is, you kind of go towards the state B. which you do not want. So what is the condition on this Vx? It should be less than Vm of inverter 2, or let's say Vm of this cross coupled inverter pair, because what we are assuming is that this Vm is equal for both. Now there's one more constraint which you will find in all these books like Rabe and Veste. So what is given in Rabe and Veste is that your Vx should be less than Vth of n. And why so? Because the moment it becomes more than Vth, here it starts to transit from A to C. However, because of this regenerative property, even if it comes close to this C, but it's less than C, like the value of Vx is less than the Vm, it will again go back to this state. However, why they take this Vx less than Vthn as the condition? So why they take this as the condition is just to have some margin. Just to have some margin. Let's say if I restrict or if I design my cells such that your Vx is less than Vthn, so my Vx won't increase beyond this point ever. So I have this margin which is like Vm minus Vx. So if any noise is present in the circuit which is less than this magnitude of Vm minus Vx, so that can also be tolerated, and we can work even with that kind of noise without affecting the state of this SRAM cell. So that is why, just to have this margin, they kind of design, or they tell that the design rule is Vx should be less than Vth of n. However, that is not the case. I mean, even if you have this Vx very close to this Vm but less than Vm, then you'll again go back to this state and you will have what is called non-destructive read. Now, how do they ensure it? So as we saw that you had this is ground, this is M5, sorry, this is M1, and this is M5, this is your VDD, and this is your node VQ bar. So the voltage of this node VQ bar depends upon the pull strength of this M1, which is kind of defined by the W by L ratio of 1, to the strength of this M5, which is W by L of 5. This ratio is a very important ratio, which is called the cell ratio, CR. And what we ideally want is that the pull strength of this 1 should be higher than pull strength of 2. That is, your pull strength of 1, pull strength of M1 should be higher than pull strength of M5, so that this node potential VQ is placed as close to the ground as possible. So we want our VQ bar, the node potential at the VQ bar, as low as possible, as close to the ground as possible. So that is the criteria, and because of that, what we'll have to do, we'll have to increase the W by L ratio of this 1 as compared to the W by L ratio of the access transistor. So for 60 SRAM cells, the first constraint on sizing of your inverters is that your NMOS transistor of inverters should be strong than your access transistors. So that is the first criteria. Now let us look at the write operation. So in write operation, what we do is we still have these bitline capacitances, CBL and CBL bar. So what we do is, first we apply VBL and VBL bar according to whatever we want to write. Right condition. So what we do is, let's say this was Q equals to 1, this was Q bar equals to 0, and now we want to force, let's write Q equals to 0 and Q bar equals to 1. Now what we want to write is Q equals to 0 and Q bar equals to 1. So what we do is, we apply ground here, so you apply VBL equals to ground, and here you apply VBL bar equals to VDD. Now, what we do is, after this step, we assert word line high to start the right kind of procedure. Again, we apply pulse, and the pulse kind of magnitude is VDD plus VTH of the access transistors, as we discussed earlier. Now, what happens is, this node tries to force this node towards VDD, and this node tries to force this node towards ground. Now, the important thing to note here is we have designed this ratio of M5 and M1 such that this node potential VQ bar can't be pulled very high. So what is the constraint that we use for defining this? We use the constraint that VQ bar should be less than VTHN if we want to have some noise margin. Or in the worst case, it should be less than VM for sure. So your VQ bar cannot go beyond this VM value. So it cannot go to VDD, and we cannot force this we cannot force this VDD over this VQ bar. However, let us look at the right hand side now. Let us look at this portion. So if you look at this portion, what you observe is that you have a circuit like this. You have this PMOS M4, you have this node potential VQ, and you have this M6, which is connected to VDD plus something, which is VTH of access transistor. This is connected to VDD. This is connected to, let's say, 0. So that this is turned on. And you have this M6 over here, which is connected to your ground. So what happens with this VQ node? M6 tries to pull it towards ground, while your M4 tries to pull it towards VDD. So what happens in this case is M6 tries to pull it towards ground, M4 tries to pull it towards VDD. However, what we want with VQ, so how VQ is connected? So VQ is kind of connected to this, to the other inverter like this. And we have at this output 0. And what we want is, we want to flip this from 0 to 1. So if we want to flip an inverter from 0 to 1, what should be the criteria? Our VQ should be less than VM of inverter 1. Right? That is the criterion. Does this make sense? So the moment your VQ reaches below this VM inverter of 1, it starts to initiate the switching from 0 to 1. However, if you want to again have the noise margin and all, what you need to ensure is your VQ should be less than the VTH of NMOS of this inverter. So when this becomes less than the VTHN of this inverter, so the inverter turns, like the NMOS turns off, and this node can easily, this node can be easily charged to VDD via this. Like the PMOS here, like the access transistor can easily charge it to VDD once this NMOS turns off. So this is the case when you require this noise margin, and this is the case which will definitely do this. I mean, which is kind of the necessary criterion is this, I would say, and this is necessary and sufficient. So it's for the case you design your sizing of this M4 and M6 such that if your VQ is less than VTHN, you'll have enough noise margin to operate as well. So that is how it works. That is why in your West or Radar, you'll find that everywhere they'll talk in terms of threshold voltage of the NMOS. Whereas even if you reduce it below the switching threshold voltage of your butterfly curve, then also it works perfectly fine. Okay, so here what we want is your VQ should be as low as possible. So we want our VQ to be as low as possible. And how can we make VQ low? So we have to increase the strength of M6 and reduce the strength of M4. So what we want is the strength of this M4 should be less than the strength of this M6. So this is called pull-up ratio or pull ratio. So what we want is the strength of this M4 should be less than strength of this M6, so that M6 is able to pull this node towards the ground more easily. So now this leads to another constraint. And what is this constraint? So for performing a write, what you want is your strength of PMOS of the inverter used in the SRAM cell should be less than your access transistor strength. Okay. Now with that, let us look at what we really call this read-write conflict. So for read operation, what we want is your strength of the access transistor should be less than the strength of your NMOS device or NMOS transistor used in the inverter. While for write, at the same time, what you want is strength of your access transistor should be higher than the strength of your PMOS used in the inverter. Now, how we typically design our CMOS inverters is, since your mobility of holes in PMOS is kind of less than the mobility of electrons in NMOS. So what we do is we kind of double the size of this PMOS as compared to the size of this NMOS. So we kind of double the width of this PMOS as compared to the NMOS, so that we have equal pull strength of NMOS and PMOS. Why we need the equal strength? Just because we want your VM to be located midway at VDD by 2. We have equal TPLH and TPHL, and noise margin high equals to noise margin low. And these are maximum only when your VM is in the middle, or the transistor VTC is kind of balanced. So at the same time, we want the strength of the access transistor to be less than the strength of NMOS, which is actually equal to the strength of PMOS. And the strength of the access transistor should also be greater than the strength of PMOS, which is actually equal to the strength of NMOS. So this is known as read-write or write-read conflict. So at the same time, for a good read or non-destructive read, you want the strength of your access transistor to be lower than the strength of NMOS. And for a good write or for a good write ability, you want the strength of the access transistor to be greater than the strength of the PMOS. So for this, how typically your inverters are designed, or how typically your S60 SRAM cells are designed, you have your strength of PMOS of the inverters as the least, as compared to the strength of the access transistors, strength of your access transistors, and the maximum strength is the strength of your NMOS transistors. So what is your take? So your 60 SRAM inverters, are they symmetric? Are their VTCs balanced? Definitely no. At the same time, you want all these transistors to be minimum sized. Why so? To increase the density. So you want all these transistors to be as small as possible, and at the same time you have to satisfy this constraint. And this kind of is the read-write conflict which you observe in your 60s SRAM cells. So how can we kind of come up with a structure where we avoid this kind of read-write conflict? So people also came up with several different SRAM cells. So nowadays you can find 60 SRAM cells. Apart from 60 SRAM cells, you can find 70 SRAM cell, 80 SRAM cells, 90, 10T. The T count can go up to 15 SRAM cells. So 15 transistors in single SRAM cell. So each of these architectures have their individual benefits. Some of them have don't have this read-write conflict. Some of them don't have this single upset event, like impact of the single upset event and all. Some are radiation hard. Some are having a very high noise margins. So those are some qualities that each of these architecture has. But one should always understand that even if you are making these 80 transistors or 80 transistors or 90 transistors, or when you are increasing the number of transistors, in your SRAM cell, you are reducing the density. So density kind of goes very low, because this is one SRAM cell is storing 1 bit, right? And you want as many bits to be accumulated in your memory as possible. So the density degrades the moment you go from 60 transistors to any of these 8T transistor or 10T transistor or 13T, whatever you have. Okay, so one of these configurations which I'm going to talk about was this 8T SRAM cell, which you can see over here. So this is the 8T SRAM cell. The benefit that this 8T SRAM cell has is that here your read path is decoupled from the write path. So if you look like this, here it's for reading, here it's for writing. And at the same time, the read path is kind of decoupled from the cell. I mean, the cell is not kind of connected to the read path. So let us look at the operation. So for operation of any SRAM cell that you may encounter, 60, 80, 10T, 13T, whatever it is, for read, what you will do is, you will first recharge your bitline and bitline bar. So some configurations may have a different bitline for read, which is the case over here. So here you can see that you have a different bitline for read, which is RBL, which will also have a capacitor here. So what we do is, we first recharge it to VDD. And then what we do is, we assert the WL high. And look at how the cell is operating. Let us just assume, like we assumed in the previous case, let us also assume here that your Q is equals to 1 and Q bar equals to 0. And now let us assert the word line high. I mean, this was the read word line. So this configuration 8T has special word line and bit line for read. And it has special word line and bit lines for write as well, which we'll discuss later. So first let us focus on this read word line, which we have to assert high, and this read bit line, which is already precharged to VDD. Let us say that our cell is precharged to Q equals to 1. Now what happens if the cell is containing 1, it will kind of turn on this transistor, right? So this transistor over here, this is on. Now once you assert your word line high, this transistor also gets on. So what it does is, it basically discharges this RBL, the potential at RBL, it basically discharges the potential at RBL to ground. So the voltage at this RBL reduces the moment you apply this RWL and you read the cell. Similarly, if your Q was 0, what would happen is, this cell would be turned off, and as such, whatever value you had at this recharge mode, that is VDD, will be retained. So that way it distinguishes between state 0 and state 1. So state 0 corresponds to VDD at your VRBL, and state 1 corresponds to ground at this VRBL. What about the write operation? So the write operation also remains similar to the 60 SRAM cell. As far as any SRAM cell is concerned, like whether it be 8T or whether it be 6T, whether it be 13T, no, basic operations remain the same. And what is there in the write operation? So you first apply VBL and VBL bar of appropriate polarity. So here, as I told, we have different bit lines for write. So we have WBL and WBL bar. So what we do is we kind of apply whatever we want to read in this cell, we'll apply this WBL and WBL bar. Second, we assert word line high. So here, as you can see, that there is this write word line which is special for this. So we'll assert this high, and depending upon whatever values are like whatever values you give to WBL and WBL bar, the cell contents will be flipped. Now here, one thing to note is, just because your read and write are decoupled, no sizing constraint is required. So it's not required. However, if you maintain the pull ratio here, you can still do the write operation faster. So that is just to make your write operation faster. However, you can also do away with that. I mean, even if you don't have this pull ratio maintained over here, this cell will work and write will be performed, because you are not sizing this node over here such that this can't go to VDD. Here there is no constraint. So this node can also go to VDD, this node can also go to ground. So here cell ratio, pull ratio are not required. And you can use minimum size transistors, you can use symmetric inverters. So that is a benefit of using 8T cell. What are the disadvantages? So let us look at the disadvantages first. So let us look at disadvantages also. So you have two word lines as compared to your 60, which has got one word line. You have 1, 2, 3. You have 3 bit lines. You only have 2 bit lines for your 60 SRAM cell. You have 8 transistors. Here you only have 6 transistors in your 60 SRAM cell. Routing of this 2 word line and 3 bit line for a single cell, as compared to routing of 1 bit line and 2 bit lines and 1 word line for this 60 SRAM cell would be very complex. So disadvantage, if I tell, first, complex routing. And the inherent disadvantage, density. So your density is going to be low, your routing will be very complex. So these are the disadvantages that you'll see in your 8T SRAM cell. So you may get an exam in the question where I give you some SRAM cell which you will be seeing for the first time, and then I may ask you to comment about the possible difficulties or possible demerits of this SRAM cell and the possible benefits of this SRAM cell. So the parameters that you look while answering those questions would be routing, the complexity of the routing, the density. Then what is advantage? You will just do this read and write operation. You will use the same steps that we have followed over here. That is, during read we do these 2 steps, during write we do these 2 steps. And if during read and write you find that there's something like there's some potential benefit of that SRAM cell, you'll have to note that. So with this, I'll end this lecture, and in the next lecture, we'll kind of go ahead and look at all the noise margins of your 60 SRAM cell. Okay, bye.